Hello and welcome back to Show Your Work. I'm Jake and today I want to take you all on a little journey showing how complicated things in math are really built on much simpler things. So we're going to start somewhere that I'm sure we've all been before, somewhere very simple, and we're going to build up to something that I'm sure most of you have not seen before. So let's get started. So what was the first operation that we all learned in math? It was just counting. Might seem weird to even call that an operation, it's just so basic, but truly, this is where it all begins. Just knowing that everything comes in an order, and if we want to count up from 2, we get to 3. If we count up from 3, we get 4. Okay, we all remember how to count. So how did we then learn addition? Addition is actually defined as repeated steps of counting. So what do I mean by that? We have these two numbers here. We're going to call the first one the base, which just means this is where I start. So I start at 2. And then the second number we call the index. And this is telling us how many times to do the previous operation. So the previous operation is counting. And though we don't have a good little symbol for counting, I'm just going to kind of use this little upside, or that little U there, to say, okay, we count 3 times from 2. So 2 counting once gets to 3, counting twice, counting 3 times. 2, 3, 4, 5. Now this might seem like a weird way to define addition, but this is actually kind of how we all learned it in the first place. When addition was complicated, we just did it by counting on our fingers. What's 2 plus 3? Well, we start at 2 and go 3, 4, 5. Count up 3. And then eventually we kind of got comfortable with addition. So we learned the next thing, multiplication, 2 times 3. Well, same pattern. What is that? Multiplication is just repeated addition. So we have the same notion of a base that we start with, and the number 3 tells us to do the previous operation, adding a total of 3 times. So I want to add 2 to itself, a total of 3 times. Again, base 2 tells us the number to do, and then the index 3 tells us how many times to do the previous operation. And we kind of thought of multiplication like this too until we got comfortable with it. If we didn't know 2 times 3, we could just count up by 2's, 2, 4, 6, to get our answer. And then we come to exponentiation, which we write as 2 to the third power, 2 raised to the 3. So how do we understand this? Well, this is just repeated multiplication. So we start with our base 2, and we multiply it to itself, index a total of 3 times. 2 times 2 times 2. And most of us actually think of exponentiation this way. Not many people have exponents memorized. When we see 2 to the 3, in our head we kind of just do 2 times 2 times 2 to get 8. Now some small details to be aware here. Notice with addition and multiplication that 2 plus 3 is also the same thing as 3 plus 2. If we start with the base 3 and do 2 counting operations, 3, 4, 5, we get to the same place as if we started with 2 and counted up 3. Same thing with multiplication. If instead of starting with 2, I start with 3 and multiply it by, add it to itself 2 times, well, that's the same thing as adding 2 to itself 3 times. But notice in exponentiation, this no longer works anymore. We had 2 to the 3 to get 8, but 3 to the 2, which is just 3 times itself, a total of 2 times, equals 9. So this is the first time that that little pattern actually breaks. Something to be aware of. Now, a great question to ask here is, This is about as far as most of us have learned, but is there any more? This is just kind of a repeating pattern here. We start with counting. Addition is just repeated counting. Multiplication is just repeated addition. Exponentiation is just repeated multiplication. So the good question is there anything after this? Is there something that is repeated exponentiation? And the answer is yes, there absolutely is. And we call it tetration. Now, there's not really a good symbol terminology for this, or at least not a common one, but I'm going to use something you might see around, and it's just moving this exponent to the left spot instead of the top right spot. So what does this mean? We have to think about it following this pattern. Exponentiation was just repeated multiplication, so tetration is just repeated exponentiation. So we have a base of 2, and the 3 says we exponentiate it a total of 3 times. So this is 2 to the 2 to the 2. A little tower of exponents. We call this a power tower in math. It's a tower of powers. So how do we solve this? We kind of have to think of it from top down. What is just this little piece here? Well, that's 2 to the 2. We know what that is from exponentiation. That's just 2 times 2, which is 4. So this whole thing is 2 raised to the 4, which is 16. So notice how the number here on the left part of our exponent tells us how many total 2's are in this power tower here. Can we keep going? You bet we can. Next we get pentation. So just to kind of keep our symbology going, though again, this is not an official way to write this, but one possible thing we could think of is moving that exponent down one more spot. So what does this mean now? So this number tells us how many 2's are going to be in the tetration tower. So this says there'll be 3 2's to tetrate. So this is 2 tetrated to 2 tetrated to 2. And we have to start to unpack what does this little mean again. So let's look at just this top part, 2 tetrated to 2. Well, this means 2 exponentiated to itself a total of 2 times. Very conveniently, this is also just 2 squared. Okay, so that means all of this is 2 tetrated to 4, which again, following our previous thing, we know is 2 raised to itself a total of 4 times. And how do we solve this? Well, we kind of start from the top. So you'll notice there's this tower of 3 2's that we've already solved before. Those 3 2's reduce to 16. So all of this becomes 2 to the power 16. And what is that number? Had to get my calculator for this. This is 65,536. So notice how quickly that grew. Just to retract here, we did 2 plus 3 to get 5. 2 times 3 got 6, 1 higher. 2 raised to the 3 was 8, 2 higher. 2 tetrated to 3 was 16, even 8 higher. And then 2 pentated to 3 is now 65,536. So we've dramatically increased here. What do you think? Can we do one more? I think we can try. Let's give a try at hexation. So we're kind of running out of a way to notate this. We've already put an exponent in the top right, top left, bottom left. The only thing that's left is bottom right. I'm going to use that for today's purposes. Just remember, this is very inappropriate. There is no official symbology for hexation. We're just kind of using this to help us understand the pattern today. So what does this mean? This number is counting how many pentation towers we're doing. So this means 2 pentated to 2 pentated to 2. So what does this mean? We have to kind of take this step by step. Again, just looking from outside in, what does just 2 pentated to 2 look like? Conveniently, and this is why I chose such small numbers here, there's a very useful fact about 2 we're using to be able to solve this. So what does this mean? This means a tetration tower of size 2. What does that mean? An exponentiation tower of size 2. So that's going to be 4. So that's just this little piece down here. So I solved inside this parentheses is 4. So now this is 2 pentated to 4. So what does that mean? That means 2 tetrated to itself 4 times. And now we got to unpack this again. So we've seen here's this little tetration of a tower of 3 2s going up to the left. We just solved that and found it was this 65,000 number. So now we know this is 2 tetrated to 65,536. What does that mean? Remember, this number tells us how many 2's are in our exponent tower. So what this all means is 2 to the 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 2. And how many of those are there? This tower is 65,536 2's tall. And now this is a number too big to even write down. It is no longer possible. So I hope that was kind of fun and interesting. Remember, hexation was just repeated pentation, and that's how we could understand it. Even though we can't write down this number, we can kind of make sense of it to some degree. Pentation, just repeated tetration. Tetration, repeated exponentiation, which was repeated multiplication, which was repeated addition, and all of it is just repeated counting. Everything in this list is just built up on counting. Now you'll notice that I used really small numbers here so that we could actually try to make sense of pentation and hexation. But notice how big these numbers would get. For example, just trying to even tetrate something like 100 tetrated to 500. Just imagine how big this number actually is. This is 100 raised to the 100th power, raised to the 100th power, raised to the 100th power in a tower that is 500 hundreds tall. And you might think, this is a little ridiculous, right? Why do we even care? These numbers are too big to write down. Do we even care? Surprisingly, we do. There actually is a number out there that has been used in a formal math proof that is so big that it makes even these numbers with this tower of 65,000 2's or 500 hundreds, all of these numbers are minuscule in compared to a number called Graham's number. And there's some great internet videos out there to tell you what Graham's number is. I'll put some links to those below if you're interested. I'll see you next time. Hey everyone, thanks again for watching. Just remember, if you or anyone you know is struggling in a math class right now, I offer tutoring in just about every math subject, including Algebra 1 and 2, Geometry, Trigonometry, Pre-Calculus, Calculus 1, 2, and 3, Calculus AB, BC, and IB, Differential Equations, Linear Algebra, Real and Complex Analysis, Formal Logic, and Number Theory. You can reach out to me at MathTeacherJake@gmail.com. You can also find me on FIverr, and I'll put the links below for that. I hope you enjoyed my video, and I'll see you next time.